The idea is we're going to have these two breakout group reports in series, and then we'll probably have some discussion about how they relate. But I think the main part of the synthesis of the whole thing is going to have hopefully going to happen tomorrow morning. And we have a whole morning before break dedicated toward coming up with some kind of synthesized experimental design that would take into account the ideas of both these groups. But I think the thing for now is that each group can kind of advocate what they think they came up with as the ideal world kind of thing, and then we'll try to merge them tomorrow morning. So give us your group's version of the ideal world.
Okay, thanks, Joe. Well, just to mention that I have the easy job here. I just have to speak, and I want to thank David Rind, who's not only one of the fastest typing scientists that I've ever met, but while I went out and had a nice bike ride, he actually put together these PowerPoint slides. And we're really going to phrase this in terms of trying to answer the questions that were set for us. The first one is, what are the most important climate change science questions to be addressed in this time frame? And we thought there that the regional climate variations, especially extremes, were important.
You want to clarify your exact time frame.
The exact,
say it again. Yeah.
The exact time frame we decided where we were probably going to do 25-year predictions from 2005 to 2030. So these regional ones in the extremes, especially, we got requests for much better precipitation extremes, which have been very difficult to predict so far. Soil moisture, perhaps. Snowpack, especially for the western US, they're very interested in that. Temperature in terms of heat events, which have been killing elderly people in Europe, as well as struggling in Chicago in the last week. Obviously in the US there is extreme interest in the future of hurricanes. Will they become stronger, possibly more frequent in a warmer world? There are potential impacts on human health through aerosols, ozone and disease vectors. Masakamoto brought up the impact on fisheries, especially for Japan, where they like their fish on sushi a lot. But also I think an important science question here would be that we could look at the magnitude of the aerosol forcing from the model, both the models and the observations, leading to, we would hope, a better indication of the climate sensitivity due to aerosols than we've had in the past. Is that correct, David? You thought that was an important point.
And sensitivity in general. If we know what aerosols really are capable of doing, we can then look at the past century better with a better eye.
Right. So he thought that was an especially important part of the science we could address.
I'll just ask a question
Yes.
about why it's easier to do that in this after 2030 time frame as opposed to the longer term.
Well, for one thing, we'll be getting data back in this next decade on what there'll be presumably aerosol observations. There will be the temperature record. So during this time frame, this is the time frame we'll get a lot more information, even just empirically, on things that will allow us to deduce the climate sensitivity.
And it's not the from now to 2030 that helps you do that. It's the analysis they have to do to spin up and calibrate the model from some past period to now. That's actually what allows you to do this. But it's higher, and as you'll see later,
It's higher resolution.
characteristics let you do that. Hopefully.
Okay, great.
So question 2 was, what models are most relevant to address these science questions in this time frame? And the two we came up with were sort of current type level 8 atmospheric ocean general circulation models, and then Earth system type models, although some components we will show or believe later are best done offline. And of course, as soon as you want to say you're going to have a much more complicated model, but you also want to do much finer resolution, then there's a real problem concerning the partitioning of the resource expenditure between these two types of models. And so we'll say a little more about that later. And fortunately, the whole group actually agreed on one thing, which was that for this particular problem, EMICs were not as useful as these sort of things, and just in the sense that if you're trying to produce regional information, regional forecasts, EMICs by their nature average over large spatial domains, so that they're not so relevant for what the science we want to do here is.
If you're really interested in short time scale, like the next few decades, I guess you also need something to do the right initialization, maybe some...
We'll come to that in a minute. That's in question 6, I believe. Is that correct?
You have to wait. Be patient.
Yeah, be patient. Because I and others are from institutions which use atmosphere-ocean general circulation models, there's institutional pressure to use these types of models, and the climate change, as Jerry made me say, we would go out to, we think, about 2030. One of the real reasons to do that is we get in this pressure, so we do these changes sort of that would affect the lifetime of policymakers. I mean, we always hear that they think about, oh, 2100, you know, who cares that much? So that was in particular, I think, why we chose this relatively short time for these predictions. And we're thinking about, or I've been told to think about, fine resolution on the order of ½ a degree for the atmosphere and the ocean. So that's considerably finer, certainly in the atmosphere, I think, than we currently have used for the present IPCC report.
Did you talk about the top of the atmosphere?
Yes, we'll come to that in a little while. And we don't have to actually wait until question 6. Here we would say we would need to, because we're now saying these are, quote, predictions, not projections, we would then say we need to start from the correct initial climate state. So this would require ocean for certain, and again, David pointed out perhaps land, soil moisture especially, so some land components that are really important, temperature, initialization. I don't know, do we have data sets to actually do that, David? Yep. There we go. We'll go in a minute. Now I ask myself, do we have data sets for the ocean? Do we know what the state of the ocean has been over there? Ron is shaking his head. If only Tony Rosati was here from GFDL, he would be nodding his head.
Won that battle. Salinity's a problem.
Okay, well, all I will say as an outsider looking at these things at the moment, that at GFDL there's one scheme, and at MIT through the ECHO project there's another scheme where they are claiming, they are reproducing for us the state of the ocean in a sort of reanalysis, like we've done for the atmosphere for years, for the ocean. And I know the ECHO one is 1990, but I think actually Tony's maybe back before that. Is he? Does he start in 1980? Pardon?
1970 it starts.
Yeah, but...
It's the XBT data set.
Right.
That's what's being used. But again, the problem is the salinity side. And the salinity really only comes in with Argo.
Right. So Tony Rosati,
years ago or something.
Tony Rosati for a long time has done this initialization because he's been interested in ENSO, so he's done it for the upper tropical Pacific Ocean. But now he is expanding that in scope and difficulty, I might add, for a sort of global ocean. And he, at this particular point, is asking the question, can we possibly initialize the ocean in the North Atlantic to get the, quote, the correct state of the North Atlantic overturning circulation. On the other hand, so there will be these ocean data sets, and so I, as a sort, could claim as a sort of user of those that maybe will nudge towards our model towards those, quote, true ocean states. We need gridded emission data for aerosols and short-lived gases would be required at this finer resolution than we've done so far. But we would still anticipate that there are people who like to do downscaling to even finer grids. Using the output of this model would do so, down to even finer resolution. So it wouldn't completely rule out downscaling work, but this, of course, would be global. So how would a very fine resolution model be developed in this time frame? Well, fortunately, we had Masakamoto here who could speak from experience. And the Japanese experience is that tuning only has to be done with respect to extremes, so that they've done some tuning of the convection and the boundary layer as they've gone down from 300K to 100K, and in the end they have a global atmospheric model with 20-kilometer resolution. So there weren't very many actual changes in the form of the parameterizations. What they did, though, was tune the parameter values within those parameterizations to go to this very high, this is 0.2 degrees resolution. And another thing that was fortunate was that their climate sensitivity for this 20-kilometer was very close to what it was for coarser resolution. So that,
not 20 kilometers, that's an atmosphere model. So
yeah.
100 kilometer couple.
Wasn't also the, did you not do the climate sensitivity coupled to a slab ocean for this one? They haven't done that. Okay, so excuse me. So anyway, from down to 1 degree resolution, they found that their climate sensitivity was a weak function of the resolution, a much stronger function of the physics and the parameter values that you put in. That result, we weren't certain would go over to other climate models. And especially if we put in some more vertical resolution.
Yeah, like I say, I know from experience at GFDL, our 1 degree model has a very different climate sensitivity than our 2. And if we move the top again or add vertical resolutions, that one's very different than the other ones also.
Right. So it's not necessarily, I believe. The Japanese have either been lucky or good, as I said, or both.
Well, ours is reasonably stable. The horizontal resolution between 200 and 150 kilometers, but the vertical resolution is another matter.
Are you saying this is going to be sort of the core set of models for AR5 are going to be like this?
No.
This is
one possibility. This is one possibility. In the Japanese higher resolution coupled models, the extremes and the hurricanes are better simulated. More, in particular, I think, was it the hurricanes or the typhoons that you actually thought were? Maybe both. Okay. But I know the Japanese were very happy with this because they thought that relevant to Japan, the typhoon simulations were much improved. Yeah. But again, that Japanese model with the higher resolution still has problems with the rainfall frequency, especially in the distribution tails, and its ENSO is not really improved compared to coarser resolution models. Is that correct? Not at all. I was trying to be nice, but he...
That was still the 100-kilometer coupled model, so they haven't run the 20-kilometer coupled. So it's unclear what the 20-kilometer would produce for ENSO, right?
Right.
No, we don't have any checking on the
Coupled model, right, yes. So the results I just talked about were 100, yeah, with an ocean resolution that was, it's 0.4 by 0.3 or something like that, isn't it?
1/4 by 1/6.
Yeah, there we go. Yeah. So the next question that, again, David made us think about was, how would a very fine resolution model be validated? So one possibility is historical simulations with the goal of regional accuracy. And that would be computationally really prohibitive. if we actually did weather forecasts or tried to do weather forecasts with it, that would require atmospheric data initialization, and that has certainly not been done with any sort of climate model, running climate model mode at this point. As we just said, the ability to produce events impacting regional prediction, especially ENSO, is not guaranteed. And I guess a sort of concern that I had in the climate system model, I'm more familiar with at the moment, we're really on a drive to try and improve the physics so that we improve the mean biases and things like ENSO. And I guess I was a little concerned that if we don't really improve our physics within these models, that these things will actually be seen as accurate forecasts, which I have a little concern about. Anybody else want to comment on that? No.
Just a comment on the first bullet. I thought that the 20 to 30 year time scale was defining a resolution and a computational requirements in a sense. Doing a historical simulation is something like 100 or 150 years.
Yeah.
Is that inconsistent with that 30-year time scale?
Well, we'll talk a little more, but what we're really thinking about, if we're going to do, well, we should do historical things, but we're going to do them for a much shorter time than that 130 years, which traditionally...
You weren't meaning the full...
Traditionally, you know, you and us have done 20th century runs have been 130 years long. That's too long for this type of resolution.
So you'd be thinking more like 1970 to 2000.
Exactly.
And then would it be, you were thinking, jumping ahead, ensembles are probably going to be coming, right?
Yeah. You are jumping ahead.
Good prediction.
I made the questions.
So, an alternative approach is to use an Earth system type model. And then we would think that if you're going to have a lot more complexity like that, you would need to keep the current resolution, or close to it, and you would add in the physics useful for the 25-year prediction time ranges. We've heard a lot here about aerosols. There's some people keen on aerosols here. They tell us that maybe you can't do those correctly without the appropriate tropospheric chemistry. Norm McFarland is here, so he always keeps telling us about stratospheric chemistry and ozone changes, so that would dictate the level at the top of the atmospheric model. He certainly likes to see that go a lot higher. GIS has also done a lot with the top at 80 kilometers.
Yeah. And for this time period in particular, the ozone hole recovery and the circulation changes associated with that's a prime player in this time period.
Right. We would want some, we've also got people here who are keen on dynamic vegetation for the health of the biosphere and possible successions, although we were thinking of those in terms of changing what the current state of the vegetation is within grid points, rather than saying the grid point, the vegetation types would move, which we thought was on longer time scales. And we would also think that you need to do something better about fire. And a consequence of all this is that this would provide more accurate assessment of climate change forcing, including the indirect effect of aerosols, which, for example, in the model I'm associated with, we've never actually put in, and other people are farther along. Hadley Center has that, GIS, probably GFDL, I think, as well. So, and Jean-Francois is always keen for us to do something about air quality assessments, so we let him say that again.
Good friends.
So those are sort of the two extremes that we talked about. Maybe the actual thing that we would propose is a compromise approach across these. So we would have finer horizontal vertical resolution than currently, but would go for simplified aerosol and chemistry routines. So that we're thinking about it would, I mean, this would still cost quite a lot more and therefore limit the number of ensemble members you could go for. Obviously, the advantage you have here is you're doing much shorter historical and predictions. But we're thinking that a sort of aerosol package would be something like a factor of 2. Doubling the horizontal resolution is a factor of 8, if that dictates your time step. And a doubling of the vertical resolution, obviously, is a factor of 2. But if you did this, we think that this would have to be in parallel with coarser resolution models that would be used for in the mode which we're much more familiar with and we've used so far in the IPCC simulations, say for historical simulations and future projections like A1B. And again, we come down to this little question that would this finer resolution model have a similar climate sensitivity to the coarser one? And I guess from what people have said, that's unclear. Anybody else want to make any comments on that? They were a lot more talkative this morning around the table. Question 3. What emission scenarios are most appropriate for this time frame? And we were told that probably the well-mixed trace gas scenarios do not differ very much prior to 2030. But for aerosols and short-lived gases, we would need finer resolution emission inventories for these regional projections than we've had before. So Steve, you said that these things hadn't been done on this sort of resolution of less than a degree before.
Not consistently and for all the things you need.
Well, not globally, for some regions.
Right, exactly. Think globally.
Right.
Yeah.
So what we're calling historical, which may well go back to about 1970, but maybe a little more. And the future emissions would have to be gridded, and we'd need some process to get these inventories for us. Is the American inventories or inventories? Inventories, thank you. So if we're going to use the sort of same well-mixed trace gas scenarios, then what we do to have different scenarios would be different levels of projection levels of projected pollutants. And those decisions were sort of needed on what emissions are required. Although the gentleman from the University of Maryland over there was talking about sort of alternate ozone precursors, maybe more interested than alternate sulfur projections. Do you want to say a few words about?
Was that me or was that you?
Oh, yeah. Oh, that.
Well, from
It wasn't anybody. No one wants to own this one.
So based on what was done for this run of IPCC, based on AOGCM, there were very wide variations on the ozone precursor emissions, and so that would be something that would be interesting to look at. Well, we thought that maybe some of the sulfur response, maybe one extra scenario might be enough.
And part of what
one higher or lower, and hope that it scales linearly.
And the issue there is the thought is that the sulfur relationship of the sulfur impacts to emissions is likely to be more linear than the ozone precursors, so there might be more interest in exploring, a range of what's going on there. And in a sense, the other issue is there's in some sense more uncertainty, in how well NOx is going to be controlled in different regions of the world, whereas for sulfur, in some regions, it's definitely going to be significantly lower over that time period. Other ones, it will be higher, but so.
But, I mean, I missed this part of the conversation, but because I was sitting in the other group. But maybe for carbonaceous aerosols, those are still kind of what you call interesting, right?
Yeah, and one of the things that I don't know if you made on the slides is that you definitely need you need the land use change in this time period. I mean, land use change, particularly in the tropics, is a key driver, and then the emissions associated with that, the burning emissions, are obviously quite important. And then fossil BCOC in various places is of interest. So yeah, there's the large number.
I think they're much more likely to differ dramatically from one group model or emission modeling group to another, right?
Right. So there's a lot of possibilities to consider. It's just a matter, how do we bound this? Yeah.
From scenario to scenario, even though the well-mixed gases are relatively similar. Yeah, because these are dependent on
But even the sulfur will be similar compared to the black carbon or to the organic carbon, I think.
The issue with the black carbon is also they're uncertain. The present day emissions are uncertain.
Yeah.
So you could even do a consistent historical through future projection with different present levels to see how that impacts things, and that would be extremely interesting scientifically. And I don't think anyone's really done that.
And then it was brought up about this is it recent or Paul Crutzen just been talking louder or more often than before about geoengineering using the sulfate aerosols?
Well, it's been around for a while.
It's been around for a while?
It's just a new flare-up.
About 30 years.
It's on a cycle.
It's back in phase now.
The Russian.
Yeah, Golitsyn was one of the first, but in the U.S. Academy report in 1992 had a huge appendix on that.
Okay, so that's something I hadn't really heard about before. So if we're going to do a mitigation strategy, that's one that could be looked at. And then what are the possible consequences for acid rain if this is done, especially in the troposphere, I guess, is a question.
But not much of one.
Not much of one? Oh, okay.
It's small compared to what we're already doing.
But the thing is that, I've thought about this quite a bit, and maybe more important is to think about what it will do to stratospheric chemistry than it is to worry about acid rain.
Yeah.
It's a small term compared to surface emissions.
That's a much bigger potential issue. Yeah.
So in this sort of compromise approach, what would be the appropriate experimental design to address the scientific questions? So the compromise approach would have more simplified extra physics in the aerosols, chemistry, and vegetation, which would change within where it is, but not migrate, and somewhat finer resolution. So that with the longer timescale issues, such as ocean biogeochemistry, land ice, ecosystem migration, would be omitted in the prognostic form of this, or done offline. The solar forcing would use just a constant value or an 11-year cycle, but with no predictions of a change in the mean variation. And I asked about volcanic forcing, so we could use something about stochastic volcanic eruptions, but everybody else thought this was less important, and most people thought you shouldn't have a volcanic eruption in the prediction between up to 2030. Although clearly if you have a large tropical volcano go off, it's going to have global climate effects. Any more comments? Question 5. What is the proper combination of ensemble scenario simulations? We know that if you're going to do regional predictions, especially of extremes, you require ensemble simulations, especially, as it says here, for hydraulic cycle changes. The number is a little uncertain, but we thought that there's been discussion that we should have at least 10 in for one scenario. You need 10 at least ensemble members in order to do these extremes, especially about water. And that sort of is exacerbated by the fact that if you're doing shorter predictions, then the climate change you get out of those is going to be smaller and therefore the determination of changes extremes is more difficult. And that's also true if you're doing it on a smaller regional scales. So we thought then that there's probably going to be one base scenario for well-mixed gases and a few for changes in the aerosols or the short-lived gases. And maybe, did we talk about that, about doing sort of, you know, an ensemble of 10 or 12 and then just one each for these? Was that the idea, David? That would be my idea, or I'm not sure, right?
We were very specific.
Yeah, okay. That would be my idea, that you take one base, do about 10 or 12, and then say there's 3 here. So that would be a sort of total of 15 members.
I have a question.
Okay.
So presumably the rationale behind the one base scenario is that they didn't differ very much until 30 years out.
Right.
But they probably do differ quite a lot in like land use and stuff like that might have a bearing on ozone precursors.
Anyone want?
So that could be related to the short-lived gas alternate scenarios, including different ozone precursor assumptions.
So those would go into the, I mean, different assumptions about land use would go into the different.
Well, or maybe we could just add aerosols or short-lived gases or surface land use changes or something like that.
We can do that. Question 6, what is the starting point for the simulations? So some historical spin-up will be required, and as I talked about before, there are supposed reanalyses of the ocean from, let's say, about 1980. So if we start before that, then what we do is we integrate up, and as we come into a regime where we have these ocean reanalyses, then I would say what we do is nudge towards those ocean reanalyses for the time we have them, say from either 1980 or 1990 up through 2005. And then, having done that nudging, you claim that the ocean is in its present state. But you have to say, yes, Jerry.
What about the radiative imbalance in the atmosphere?
Oh, we'll get to that.
Okay. So the emissions data is best from 1980. So we'd thought about starting at about maybe at 1970, and then David pointed out that in fact, if you the Earth was probably in a better radiation balance in about 1950, because then you would avoid the more drastic warming from 1970 onwards. So we got a number of dates here: 50, 70, 80, and 90. It was unclear to us what exactly the best strategy was, but I think 1950 would be an absolute maximum that you would do. Rather than 1870 or 1850 that other groups have done, or we've done in the past. Of course, what we're trying to do here, is you try to get the atmosphere balanced up at 1950, and then you go through the scenarios and try to reproduce the last half of the 20th century. That's what you do. But when you're doing these, if you're going to do that, then you do need the data, the forcing data sets for these historical, what did we call them? Historical spin-ups. So the ozone, land use, biomass burning, fire, black carbon, and we thought actually with these shorter predictions, it was actually much more important that they get smoothly merged with the scenarios to use for the future from 2005 onwards, because if you had an imbalance there, it would be more important for shorter predictions than if you're going for longer integrations. So we actually sort of punted a bit on exactly when we'd start. Then it was getting towards noon by this time, so we were getting hungry. But what we then said was, we came out and said, if we did all that with this model, how many years of integration would you need? And we came out to sort of a minimum of about 1,000 years. So that, we then said, how many years a day can you integrate on present computers? And I forgot how did we estimate that? But it was something like 4 machine years, because you thought you'd get...
Based on what we did at a lower resolution with a simpler model on a dedicated supercomputer,
right,
and then did the back of the or the in our head calculation.
So if you get it, if you get in a year a day, and you want to do something over 1,000 years, then it's about 4
So
years.
Phil, we'll task you with getting out the envelope tonight and actually.
Doing it a little more carefully.
I mean,
we can make it in whatever number you want. Tell me what number you want.
But it seems to me that with this type of exercise, you can very, very easily say you need as much computer time for the sorts of exercises we've done before for more traditional IPCC without any trouble. In other words, we can match that other working group without any trouble, I think, in your computer time requirements. So.
And you did make the point, this is sort of ignoring the needs of the other group doing the longer term projections.
Right.
As far as the machine goes.
Yeah.
People.
Exactly. Yeah.
But this is on current machines.
That's on current machines.
So for 5 years from now, you're supposed to get.
Claire, if you want to work on making our code work on massively parallel machines, we'll be delighted to have you work with Phil and getting those work on petascale. That, of course, that is present-day machines. I'm glad someone's optimistic in this. Clearly, we're going to get more computer power. Quite whether these petascale things that I've heard about are really realistic in the next, before we do the next IPCC, is unclear to me. Pardon?
Why don't you use the term useful? We will get more computer power.
I think
we'll get more useful computer power is, like you said, a very open issue at this point.
Well, and put it in context too. At NCAR, I believe what Bill Collins did just prior to turning the reins over to Peter was to make guesstimates about what we would need, and the guesstimates required a factor of 5 or so increase in computer power. And when that number was presented to our computing people and maybe to the people that are represented by DOE, for example, also, they said, we can probably provide you with that kind of an enhancement. Is that
a factor of 5 to 10,
yeah.
Like a factor of 1,000, which is what the petascale initiative is talking, is absolutely enormous.
Right.
Yeah. Because these things, these petascale machines, there's not any clear evidence, any concrete evidence. The types of models we use and many other simulation fields use will be able to scale to make use of these machines no matter how hard you work. And it's not even clear that the programming paradigms exist on which anybody can make use of these new systems unless they're ridiculously parallel.
So in that context, if our back of the envelope was okay, of 4 dedicated years on today's machinery, we get a factor of 5 enhancement, we're down to a year's worth of simulations for all the things Peter outlined, and that's actually a feasible kind of a time frame for this experiment.
Yeah, the CCSM for this current IPCC, I did it from Jim Hack's numbers and some of the other things, took the equivalent of a cheetah year, which was a 4.6 teraflop IBM class machine, dedicated running for a year. That was, if you summed all the resources for the, and that wasn't the development cost. That was just the simulations that were used for the experiments themselves. It was about a 4.6 IBM teraflop year, if you bundled it all up.
But
So you're talking about a 30 teraflop year.
But independent of the computing power, it seems to me, do we have the people power and enthusiasm to do these two different types of simulations? That is unclear to me.
That's also, when you deal with issues, it's also the amount of data that the models are going to produce and how you deal with that. It's you could get the clock cycles but not get the information off the machine to a place where you can analyze it.
Yeah.
There's all sorts of things that go along with this.
Ron, you had a comment.
Yeah, I was going to say from at GFDL, I actually can tell you, is assuming that we don't get any new computing from somewhere, you know, falls out of the sky on us or something. we just went through a procurement and we're about ready to go into it. And our factor of increase over what we have now is a little less than 2 up to the year 2009, and then it's going to be a little around 3.5 or something like that.
Over today, or 3.5 above the
no,
2?
3.5 over today. In 2009. But the root issue is we have less money now than we did 2 years ago for computing. That's why the increase is smaller.
It's a slightly different approach than that of the Hadley Center, where the decadal prediction is done with HCM3, so still the old version of the model, just to be able to run more on some ones.
But does that have aerosols and indirect effects, for instance? Land use change? It probably does, doesn't it?
It does have some aerosol, a bit outdated now. I'm not sure about land use change.
And what resolution was that?
Well, I haven't been with the Hadley Center for that long, so HCM3, do you know the resolution?
It's about a 2-degree atmosphere and a 1-degree ocean.
No, that's closer than that.
No, it's close to it, right?
Yeah.
Well, that is the HCM3 ESM the same resolution as the physical time frame?
No, had CSM3 is 1.25 squared in the ocean.
Right.
And in the atmosphere, isn't it 2.5 by something, so that they fit into those squares? Isn't it 2.5 by 3 3/4?
It's 8
yeah,
grid
that's right.
boxes in the ocean per.
No, I thought 6.
It's what the resolution Peter showed yesterday in his public lecture. Right.
Right. I think it's 2.5 by 3 3/4 in the atmosphere, 1.25 in both directions in the ocean. That's what it is. Yeah. Okay.
Are these simplified burst system models? This second approach you're talking about is that are those models different than the models we're talking about for the longer term runs?
Yes.
Well,
Yes.
I think the answer is yes, and we'll see how.
Would you call them simplified?
Most EMICs don't have
intermediate
PDs
complexity.
they're
not
not
the Earth system
GCMs.
There's Earth system models of intermediate complexity.
These are EMICs, right? But I mean, the ones we're talking about are not.
Wait, what are you saying are EMICs from?
Just lower resolution.
Ones that don't have a GCM atmosphere.
Well, they have
I mean, are you suggesting that anything Peter showed was an EMIC? Or were you
No.
suggesting that the calculations that we're going to hear about for the other group were EMICs?
Neither. I thought I was. Maybe I misheard your question.
I think so, because I thought that the
Oh,
model
the ESM system. I'm sorry, I misheard your. I didn't understand your question.
Well, yes, because in this one we said all those things like carbon cycle wouldn't be in there and whatever, and I believe ocean biogeochemistry. I'd be very surprised if we're not going to hear about those now.
But you had succession.
Yeah, because that's what people thought was important for the aerosols. The
Also,
That's not the right word, though.
no, what was it? It was focused on one of those.
It was just growing and dying in place.
That's right.
I don't think that's succession, though, is it?
Yeah,
Succession was something.
Well, simpler layers.
Yeah, I think what's the right word for vegetation growing and dying in place but not moving? It's not succession, is it?
Well, succession is the change in the community structure over time at a place.
at a place.
And it's usually associated with changes in the plant functional types through time.
I mean, some sort of vegetation response to climate is needed, and exactly what, and particularly to land use change and fire over this period. But exactly what that is and how that compares to the, what would be in the longer runs, it's not quite clear if that's really different or not. Especially if it's not a huge
I don't think
expense.
we were concerned with carbon storage, for
Yeah.
example, or
But-
with evolving from pines to aspen.
But it may be that whatever's in the long model may be fine for this, and if it's a parallel development, that works great because you don't want two different things.
But you were going to do fires without carbon.
Yeah, because we cared about the sort of instantaneous release of.
Care about the aerosols from fire and the albedo changes, the water feedbacks between the vegetation and the climate. Yeah, the carbon's not important, but for this.
But it's okay if it's not too costly to do it the right way.
Right.
Yeah, because if you're going to improve your ability to simulate extreme events, then you're probably going to have more fire. You're probably going to have...
Well, I think the overall issue with this whole approach is someone said that, well, we need finer resolution to do regional climate. And, that's great in principle, but, we already know that, the models do have trouble with extreme events now. So there's this question of, is it worth expending the resources to do this, just to get, another result that you may or may not have more faith in. You would probably learn useful things, but this is really the question: is do you learn enough doing this, given the resources it'll take, compared with doing what your mainstream brand, your other, in other words, you're bifurcating your development efforts. You're doing this higher resolution model with some of the new physics in it, to do one thing, and it takes a work to do that. You've got to retune it, and you've got to calibrate it, and you've got to do the runs. So I mean, just from a, not somebody that's pushing for this, I think that's an open question whether, do you get enough out of that to make that worthwhile? And that may be an individual group decision whether the resources are there to do that. And I would just guess that, it may be a rather limited set of groups that decide to do that. So now there may be some groups that only focus on that decide finer resolution and partial physics, and some groups that aren't going for the full Earth system models approach. And in a sense, maybe that's a useful way.
I guess as a comment on that, to me it's a research issue from the physical climate side. Is there any predictability in the initial, do we have the ability to initialize these models to the present day ocean or not? That's a research question. And if we do we get any predictability in anything that we really care about on decadal or longer timescales? And that's another research question.
Right.
So both of those seem like it really hinders a coordinated effort in some sense, because there's fundamental research questions that we don't know the answers to when you're trying to design some sort of core common activity.
So if there's fundamental research question, does it make sense to do it with a higher resolution model, which taxes the system that much more? Maybe if there's really a fundamental research questions that need to be answered to get at this goal,
but there's all I'm saying, there's other goals that are on the aerosol side and the chemistry side that you could get at. But in terms of predictability of the climate system, which is a lot of the modeling groups are going after, it's unclear whether you can get much.
Well, in that goal in particular, maybe the answer is it makes more sense to do it in the regular resolution model, so you can explore those in less computer years' time. And then the question is the resolution just to get aerosols, which there's also being worked on in the other model. And
yeah, I mean, the thing is, groups are working on initialized AOGCM type models, so I think that's going to happen. And all these interesting research questions are still going to be involved, but like we saw last night, the big part of what's going to happen in the next 30 years we're already committed to anyway. So as long as you can get the radiative imbalance and something that looks like the initial state of the ocean in there, it's not going to make a whole lot of difference. And you're going to be looking at, basically it's a question of what are we going to have to adapt to.
People are, at least the talk that I've heard, they're trying to assess the initial state of thermal circulation and give you a warning if the thing was going to collapse, for example, if you make these predictions. Or if you make none of these predictions, you start having skill, you would have convince yourself that you actually know what the initial state of thermal circulation is.
Yeah, yeah. I mean, what hinders you, as you point out, if we don't know what the salinity is like historically, then you can't do the historical runs. You have to wait till we get the Argo floats, and then you can only do projections. But I mean, that's kind of another issue.